Hey everyone! Welcome back to Bug No Jutsu, the place where we battle tricky bugs and sharpen our coding ninja skills. Today, we're going to solve an interesting problem from LeetCode, problem 3202, find the maximum length of valid subsequence 2. At first, it might look like a simple greedy or sliding window problem, but don't be fooled, it has a really elegant solution using dynamic programming and hash maps. By the end of this video, you'll not only understand the solution, but also get key insights into how to approach similar problems where you're working with pairwise conditions and subsequences. So, let's get started. In this problem, you're given an array of integers called nums, and a positive integer k. Your task is to find the length of the longest valid subsequence, but there's a twist. The subsequence must follow a special pattern. When you look at any two consecutive elements in the chosen subsequence, say, the first and second and third, and so on, the sum of each pair, when divided by k, should always leave the same remainder. That means, as we move through the subsequence, each pair of consecutive elements should behave the same way when their sum is divided by k. It's like the subsequence has a consistent rhythm or pattern when it comes to these pairwise sums. And remember, a subsequence allows you to skip elements from the original array. You don't have to pick elements that are next to each other, but you do have to preserve their original order. Your goal is to find the maximum length of any such subsequence where this rule holds true throughout. Let's walk through the given example, nums equals 1, 2, 3, 4, 5, and k equals 2. We're trying to find the longest subsequence where the pairwise behavior, specifically how two consecutive elements in the subsequence add up and relate to k, stays consistent. Let's start by choosing the first two elements, 1 and 2. If we add them, we get 3. Now, when we divide 3 by 2, we're left with a remainder of 1. That becomes our reference pattern. Next, we try to extend this subsequence. Let's add 3 as the next element and check how it pairs with 2, the previous element. 2 plus 3 is equal to 5, and again, dividing by 2 gives a remainder of 1. Perfect, same as before. So we can keep going. Now include 4. The previous element is 3, so 3 plus 4 is equal to 7. Dividing 7 by 2 leaves us with 1 again, still consistent. Add 5 now. The previous element is 4, and 4 plus 5 is equal to 9. Which also leaves a remainder of 1 when divided by 2. So we've gone from 1, 2, all the way to 1, 2, 3, 4, 5, and every pair of consecutive elements behaves the same way in terms of how their sum interacts with k equals 2. That makes the entire array a valid subsequence, and since it contains 5 elements, the final answer here is 5. This example shows that if we can keep finding elements where the pair behavior stays the same, we can grow the subsequence longer and longer. The approach we use here revolves around dynamic programming with hashing. Since the problem is about finding a pattern between pairs of elements in a subsequence, we try to track sequences that follow the same rule. We begin by looking at every pair of elements in the array. For each pair, we calculate the sum of those two elements and check what remainder it leaves when divided by k. This remainder acts like a group label or pattern ID. Our goal is to find the longest chain of numbers where every consecutive pair belongs to the same group, meaning, they all give the same remainder when their sums are divided by k. To do this efficiently, we maintain a hash map, kind of like a notebook, where for each unique combination of a remainder and the ending index of a subsequence, we store the length of the longest valid subsequence that ends there and follows that specific pattern. Now, as we go through the array, we check every element with all the previous elements to see if we can extend any existing valid subsequence. If the pair formed with a previous element shares the same remainder pattern, we can continue building on that subsequence by increasing its length. If not, we consider starting a new sequence from that point with a length of 2, because a pair is the minimum size needed for the condition to apply. During this whole process, we keep updating the hash map with longer and longer subsequences whenever possible. And at the end, we return the maximum length we've found. This method allows us to explore all potential subsequences efficiently, while ensuring that we only track those that follow the rules. It's a great example of how dynamic programming and hashing can be combined to solve what looks like a combinatorial problem in an optimized way. This solution has a time complexity of n square, because we check every possible pair of elements in the array. For each element, we look at all previous elements to see if we can extend a valid subsequence based on the pattern of their sums with respect to k. The space complexity is n times k, since we use a hash map to store the longest valid subsequence ending at each index for every possible remainder when two numbers are added and divided by k. While that sounds like a lot, it's actually quite efficient and avoids the need to check all subsequences individually, which would be far slower. This problem highlights the importance of focusing on pairwise relationships rather than individual elements. It teaches us to think in terms of how elements interact, in this case, through the remainder of their sums, and use that as a pattern to track. It also reminds us that subsequences don't need to be contiguous, which opens the door to more flexible approaches than greedy or sliding window methods. Using a hash map with dynamic programming to store the state of patterns is another key insight. It helps us avoid unnecessary recomputation and makes the solution scalable. And finally, treating modulo results as pattern identifiers is a clever strategy that can apply to many other problems involving repeated behaviors or constraints. And that wraps up our deep dive into LeetCode 3202, find the maximum length of valid subsequence 2. I hope this helped you not just solve the problem, but really understand the thinking behind it, from analyzing patterns between pairs to applying dynamic programming with hash maps in a clean, scalable way. If you found this video helpful, don't forget to like, subscribe, and tap that notification bell so you don't miss future breakdowns. Have any questions, doubts, or want me to cover a specific problem? Drop it in the comments. I read and reply to every one of them. Thanks for watching, and until next time, keep practicing, keep learning, and as always, debug like a ninja. This is Bug No Jutsu, signing off.